As we have discussed one numerical on the vapor compression refrigeration cycle, today we will take next numerical on the vapor compression refrigeration cycle. The numerical is the R22 refrigeration system operates between minus 15 degrees Celsius and 40 degrees Celsius. The mass flow rate of a refrigerant through the system is 0.2 kg per second. The condenser is subcooled by 5 degrees Celsius and the vapor leaves the evaporator with a degree of superheat as 10 degrees Celsius. Determine tons of refrigeration, power required, COP and heat rejected in the condenser. And for that purpose they have given here the formula property table. That property table corresponding to the temperatures minus 15 degrees Celsius and 40 degrees Celsius. So for minus 15 degrees Celsius, the properties pressure is given 2.964 bar, enthalpy of liquid is given 28.36 kilojoule per kg, enthalpy of vapor Hg is given 245.36, entropy of liquid is given 0.115, entropy of vapor is given Sg 0.9555, and specific heat kilojoule per kg is given, that is 0.64. Similarly, corresponding to 40 degrees Celsius saturation temperature, the pressure is given 15.267 bar, enthalpy of liquid is 95.40 kg per kilojoule, enthalpy of vapor is 261.38 kilojoule per kg, entropy of liquid is 0.3466, entropy of vapor is 0.8767, and specific heat is 0.82 kilojoule per kg Kelvin. Now if you read this problem carefully, the refrigerant used is R22 and that R22 system operates between the temperature limits as minus 15 to 40 degrees Celsius, means evaporator temperature is minus 15 degrees Celsius and condenser temperature is 40 degrees Celsius. The mass flow rate of refrigerant is given as 0.2 kg per second and the condenser is subcooled, please remember this point, subcooled by 5 degrees Celsius and the vapor leaves the evaporator with a degree of superheat as 10 degrees Celsius. Now just focus on the last two lines. The condenser is subcooled by 5 degrees Celsius. Condenser is subcooled by 5 degrees Celsius, means the point 3 is extended inside the condenser, or that point number 3 is extended inside the liquid region up to next 5 degrees Celsius. Up to next 5 degrees Celsius means T3 here in this case, that T3 temperature is T3 dash plus 40 degrees Celsius. So first we will draw the pH chart, but here pH chart is somehow different because here they have given the subcooling is given. So that's why the point 2 to 3 line is extended inside the liquid region. So 2 dash is the condenser pressure line which intersects the saturation vapor curve. 3 dash is the condenser pressure line which intersects the saturated liquid curve, and 3 is the condenser outlet point. 1 is the compressor inlet, 2 is the compressor outlet. But here they have given the vapor leaves the evaporator. Please remember, vapor leaves the evaporator with a degree of superheat as 10 degrees Celsius. As we have known that the exit point of the evaporator is point number 1 and that point is superheat point. Superheat means that point 1 is always lies on the curve, but if the superheat term is given, that point number 1 is shifted into the vapor region. So here that is shown here, one point is shifted into the vapor region. It is not on the curve. So that curve point is known as 1 dash point. So here what is the given data? T1 dash is given because it is on the saturated curve. So T1 dash is equal to minus 15 degrees Celsius. So it can convert it into the Kelvin, which is equal to 258 Kelvin. T2 dash is equal to T3 dash. So T2 dash is equal to T3 dash. That temperature is 40 degrees Celsius. So 40 plus 273 is equal to 313 Kelvin. Mass flow rate is given 0.2 kg per second. Now we have to calculate the T1 and T3. So T3 is what is T3? The point is inside the liquid region. So and we know the subcooled by 5 degrees Celsius, but means T3 dash minus 5 degrees Celsius, we will get the T3, and the temperature leaving the condenser is T3 is equal to 308 Kelvin. Similarly, the degree of superheat is given. Degree of superheat means T1 minus T1 dash, and that is equal to 10 degrees Celsius, and T1 dash is minus 15 degrees Celsius. So T1 is equal to 10 plus 258 is equal to 268 Kelvin. Hope you have understood these points. Here the subcooling is by 5 degrees Celsius, and we know that the temperature is on a pH chart, temperature is increases from left to right. So T3 dash minus 5, you will get the T3, and T1 minus T1 dash is equal to 10. So if you are getting the T1 is equal to T1 dash plus 10. So now the three temperatures are known. T1 is known, T2 is known, and T3 is known. Now same procedure, we have to calculate the H1, and H1 is equal to H1 dash plus Cp into T1 minus T1 dash. So H1 dash is H1 is on the evaporator pressure, and the evaporator temperature is minus 15. It is on the vapor side. So the minus 15 degrees Celsius vapor side enthalpy, that is H1 dash is equal to 245.36 plus Cp on the same line, that is 0.64, multiply by T1 is 268 minus T1 dash is 258. So the difference is 10. So therefore H1 is equal to 251.76 kilojoule per kg. H1 is equal to enthalpy at entry of the compressor is 251.76 kilojoule per kg. Now similarly we can calculate the H2. So H2 is equal to H2 dash plus Cp into bracket T2 minus T2 dash. Now again H2 dash, it is the point on the some condenser pressure line and which intersects the saturated vapor curve. So the saturation temperature on the condenser pressure is 40 degrees Celsius, and on that 40 degrees Celsius the vapor side enthalpy is 261.38 plus Cp on that same line is 0.82 into bracket T2 is not known, and also T2 dash is 313 degrees Celsius. So this equation is H2 is equal to 261.38 plus 0.82 into bracket T2 minus 313 Kelvin. Here two unknowns are there, so we will mark here equation number 1. Now consider the process 1 to 2. 1 to 2 process is the isentropic compression process, so which indicates S1 is equal to S2, and S1 is calculated as S1 is equal to S1 dash plus Cp into bracket ln of T1 upon T1 dash. The same formula we have used in the last numerical for the S2. So here S1 is equal to S1 dash plus Cp into ln of T1 upon T1 dash. Here if the point 1 is directly plotted on the saturation vapor side, so that we can directly calculate the entropy. But here that point number 1 is offset in the saturated in the superheated region. So S1 is equal to S1 dash is the evaporator temperature, and that vapor side entropy is 0.9555 plus Cp on that same line 0.64 into ln of T1 is 268 divided by T1 dash is 258. So therefore S1 is equal to 0.9798 kilojoule per kg. And also we know that S1 is equal to S2. So if we can use the same formula for the S2 entropy at point number 2, so therefore S2 is equal to S2 dash plus Cp into ln of T2 upon T2 dash. So S2 is 0.9798 is equal to S2 dash is entropy at the condenser pressure line corresponding to the minus corresponding to 40 degrees Celsius on vapor side. So it is equal to 0.8767 into ln of T2 upon 313. T2 dash is 313 Kelvin. So after simplification we will get the value of T2 is equal to 354.94 Kelvin, or approximately equal to 355 Kelvin. So if we have taken the 354.94, so similar equation we are getting in terms of H2. So therefore H2 is equal to, if we put that value in equation number 1, so therefore H2 is equal to 261.38 plus 0.82 into bracket T2 is 354.94 minus 313. So therefore H2, the enthalpy at point number 2 or enthalpy at the exit of the compressor is 295.76 kilojoule per kg. Now if we apply the energy balance equation for the heat exchange, so we can write here the heat given by the warm liquid. Please remember, if we are observed this is a closed loop system, and if we apply the energy balance equation, the heat given by the warm liquid or the hot liquid, which is equal to heat gained by the cold vapor. So therefore H3 dash minus H3. So please remember this part, that H3 dash minus H3 means that subcooled region is equal to H1 minus H1 dash, that is a superheat region. Please remember the point here, we are equating the subcooled part and a superheat part. Subcooled part is enthalpy H3 dash minus H3 is equal to H1 minus H1 dash. So all these enthalpies are known, so only H3 is not known. So therefore H3 dash is 95.40 minus H3 is equal to 251.76 minus 245.36. So therefore H3 is equal to 89 kilojoule per kg. And also we can know that 3 to 4 process is an isoenthalpic process. So H3 is equal to H4, 89 kilojoule per kg. So total refrigeration effect is Mr into H1 dash minus H4. Please remember this point, because the refrigeration effect is observed up to the saturation vapor point. So H1 dash minus H4. H1 dash is 245.36 minus H4 is 89, and mass flow rate is given as 0.2. So therefore refrigeration effect is equal to 31.272 kilowatt. 31.272 kilowatt. If you divide by 3.5, you will get into the tons of refrigeration. So refrigeration effect is equal to 8.89 TR. 8.89 TR. So now second part we have to calculate, that is the power required. So same formula. So W is equal to Mr into bracket H2 minus H1. So mass flow rate is 0.2. H2 that we have calculated 295.76. Again H1 is 251.76. So therefore the power required for the compressor is 8.8 kilowatt, 8.8 kilowatt. So if you multiply by the 1000, you will get into the watts. Now COP is equal to the refrigeration effect divided by power required. So refrigeration effect is 31.272 and power required is 8.8. So therefore COP is equal to 3.55. And last term, that is a heat rejected in the condenser. Heat rejected in the condenser is calculated as QR. QR is equal to mass flow rate of refrigerant into how much heat is rejected from point number 2 to point number 3 dash. So H2 minus H3 dash. So M mass flow rate is 0.2. H2 is 295.76 minus H3 is 90, H3 dash is 94.40. So therefore heat rejected in the condenser is 40.272 kilowatt. So in this way we have calculated all the parameters. Here only additional thing is given as subcooling and superheating. So subcooling and superheating, so we have covered here the two different criteria of the vapor compression refrigeration systems. First numerical is regarding with the plain numerical, and the second numerical is regarding with the subcooling and superheating. So in either way you can solve these problems, or sometimes the questions can be asked on this. Hope you have understood this.